Okay, so today what we're going to do is we're going to finish up the sort of chapter 19 and 20 material. And really the material we're talking about today is going to be one of those reoccurring themes that we'll talk about it in each of the chapters hereafter for the organic chemistry stuff. And some of the stuff will even creep into the bio chapters or the energetics chapters and things like that. And the topics for today are one of them that we already know pretty well, which is intermolecular forces. We're going to introduce you to a sort of a new intermolecular force, one that we kind of glossed over first semester, but we'll mention and go into a little bit more detail this semester because we see it a couple more times. And then we'll take a look at solubility and melting points and boiling points for various types of compounds. And unfortunately for just alkanes, alkenes, and alkynes, it's kind of boring because the only functional group or the only thing we have in the molecule is basically carbon and hydrogen, so it's not that interesting, but it builds us a base to go on to the functional groups that have more interesting interactions on it. So let's take a look at the intermolecular forces. First off, what is an intermolecular force? I might pick on Jasmine a little bit since this is a review for everyone else. Jasmine, do you remember what IMFs are? Meaning, should I go into more detail or less? You remember what it stands for? Yeah, intermolecular forces. So what it is it's the forces between molecules. So it's the force between molecules, or forces, I guess. And it's primarily responsible for, first semester, we talked about boiling points and melting points. We talked about vapor pressures. We don't tend to talk about vapor pressure too much second semester. First off, it's hard to measure, and second of all, if we just talk about boiling points and melting points, you get about the same information as you would talking about the vapor pressure of something. Although, certainly we can make some comments like in class, did you notice it got a little bit smelly? What does that mean about the intermolecular forces in the compounds we were testing? They're what? Well, they're weak, right? So the intermolecular forces are weak. It's easy for the molecules to be in the vapor phase. They stink a lot. Or the stink part is probably more a part of the molecule, but the fact that we can smell it is because so much of it has evaporated already. Meaning most of the molecules that we talk about are going to have very high vapor pressures, meaning they evaporate pretty readily. So that's as opposed to intramolecular forces, which are things like our ionic bonds and covalent bonds, right? So this is between molecules, not what's holding the atoms together. And there were 5 of them, and you guys are familiar with 4 of them, so we'll just start with them. Which one was the weakest? Yeah, London dispersion forces. I should also point out that I'm going to post a link or two to some outside materials maybe on some of these topics that they say the same things I'm saying. Sometimes they say it a little bit more, sometimes they say it a little less, sometimes they say it a little bit differently. But if you're just kind of reviewing and you've already read the book and you've already listened to the lectures and everything else and you just want another take on something, those outside resources are pretty good. And you'll notice that sometimes they use slightly different words, like they often refer to intermolecular forces, and I should maybe put this on the previous slide. They sometimes refer to those as van der Waals forces, because he's the guy that sort of did them. And sometimes they'll refer just to London dispersion forces as van der Waals forces. Sometimes they'll talk about most of the intermolecular forces as van der Waals forces, and then some of them they'll talk about being electrostatic. And so how people divide them up and the nomenclature they use is a little sloppy, unfortunately. So, you know, if you do read outside forces or outside stuff and you see them talking about van der Waals forces, and it sounds an awful lot like they're talking about London dispersion forces, it's probably because they are. So what do we know about London dispersion forces? That's the weakest. Now, we always say that, but we have to be careful. It's the weakest force, right? But what's unique about this force as opposed to some of the other forces? Because it can be it's the weakest force, but it can also sometimes in certain molecules be the most important force. So weakest is referring to its strength, right? And the importance of it is if there's no other forces, it's pretty important, right? Even if it is weak. But it can also be, you know, so that it really is what is responsible for, you know, most of the attractive forces between molecules. So there's one additional point I'm trying to get at here that we should remember for sure. What is that? Big versus small molecules. Does that ring a bell? Remember, it's proportional to size. So that's a crappy looking proportional size. So that means that we have an increasing London dispersion force as we have an increasing size of the molecules. So for really large molecules, while London dispersion forces might be the weakest force, if you have a huge molecule, it might be the most powerful attractive force between two molecules. And so we'll see that when we're talking about all these intermolecular forces and the effects they have on boiling points and melting points and solubility, that size will matter in some cases. We should throw in here that this is due to an instantaneous dipole, meaning it's very short-lived, and that's why it's very weak. And then if we're drawing examples of this, probably the classical example, because it's the easiest one to draw, is methane, in which case we simply have an attractive force between two methane molecules. And it's tough to draw this one really exactly. I might just draw it as a bunch of dotted lines simply because it's not between any two specific parts of the molecule, it's just simply between the two molecules as a whole. And so remember that dotted lines are what we use to represent attractive forces between molecules, whereas the solid lines are the bonds between the molecules. So I want you to really focus on the fact that it is the weakest, but don't forget that it's proportional to size. If I have a big enough molecule, it's going to be the most important force, and it's going to control the boiling points and melting points, kind of. What's our second intermolecular force? Yeah, dipole-dipole. And I guess I should also start putting up the abbreviations that I use for these, because I very rarely write dipole-dipole and London dispersion forces fully out. We always talk about LDFs and DDs and things like that. And what are dipole-dipole attractions? Yep, that's part of it. So the idea is that we have an asymmetric distribution of charge. And remember, that's what we call a dipole on two molecules. Therefore, they behave like magnets. And that's where when we draw them, for instance, if I take a look at, let's see, let's pick a good molecule, HBr. This has got a partial negative, this has got a partial positive, and that's going to be attracted to another molecule that has a partial positive and a partial negative. Or the other way we tended to draw these was we said that if we kind of make the size of the area around each atom kind of pretend that those are the electrons, then this is indicating that there's an excess of negative, this is indicating an excess of positive, and that'll line up to another HBr molecule like this. Now these are also proportional, not to the size of the molecule, but to the size of the dipole, which really is, for us, mostly related to the difference in electronegativity. So if there's a big difference in electronegativity between the two atoms, it has a larger dipole than if it has a small electronegativity difference between the atoms. Now, we're not really going to get into strengths of dipoles too much, in that we're only going to talk about a few functional groups that have dipoles, and we'll simply label them as weak or strong. We won't talk about exactly why they're weak or strong. We won't look at anything beyond that. And so really at that point, you're just kind of memorizing which ones are weak and which ones are strong, and not worrying about sticking numbers in there and things like that. Although worst case scenario, you could probably look up all the electronegativities and make a pretty good guess too at it. So these have to have an asymmetric distribution of charge. Let's talk about that a little bit. So what are some clues that we have an asymmetric distribution of charge? What should I be looking for in those molecules? We should be looking for asymmetric molecules, right? If we have very symmetrical molecules, then we have no distribution or difference in charge, right? One of the ways we saw that is when we looked at various isomers like cis-trans isomers. And here we'll even make it more exaggerated. We'll put a chlorine. That there's a difference between these two molecules, right? Because one molecule is much more oops, got some extra lone pairs in there. That's okay. One molecule is much more symmetric than the other molecule, right? So which one of those is dipolar, meaning it has an asymmetric distribution of charge, and which one of those is nonpolar? Which one's dipolar and which one's nonpolar? So I've got the cis isomer here, I've got the trans isomer here, and I want to know which one's polar and which one's nonpolar. Yeah, so this has got a dipole. This is nonpolar. Because the dipoles for those chlorines are pulling in the opposite direction, whereas the dipoles for the chlorines in these bonds are pulling in the same direction. So one of the key things we have to do is look for asymmetric molecules. You know, another example of that is that even though carbon dioxide has dipoles, and they're pretty strong ones because oxygen really likes its electrons, this is nonpolar due to symmetry. Meaning the molecule is symmetrical, therefore it's a nonpolar molecule, even though it's got partial positives and partial negatives. One of the reasons carbon dioxide is a gas at room temperatures is simply because it is nonpolar. If it was somehow polar, if that shape was somehow different, carbon dioxide might be a solid, in which case life on Earth would be a little funky, because most of our atmosphere that's normally CO2 would either be something else, or it'd be thicker maybe, or something weird like that. So really, when we're looking at dipole-dipole, we're looking at the difference in electronegativities, and you get that chart on your cheat sheet. And then we're also looking if molecules are symmetrical or non-symmetrical, right? What's our third intermolecular force? Yeah, hydrogen bonding. Did you have a quick question? I can go back. So what's hydrogen bonding? Yeah, it's a extra strong dipole-dipole attraction. And so we kind of give it our own category. And why is it extra strong? Well, yeah, but I mean, why is this specific case of it extra strong, kind of? Remember, hydrogen only has one electron, right? And so hydrogen makes kind of, I'll call it a double plus plus there, if it's attracted to certain atoms, right? Meaning, since it only has one electron, if that electron is spending a lot of time around another atom, then the positive charge on that hydrogen looks kind of extra large, so we're going to have an extra strong attraction between it. And what does hydrogen have to be bonded to? Yeah, bonded to a small, highly electronegative element like oxygen, nitrogen, or fluorine. And so what that's saying is that if we just look at this bond right here, that this has got an extra strong dipole to that oxygen. And normally we're not going to write it as double plus plus when we draw pictures and everything. I'm just trying to exaggerate the fact that it is extra large. And really my pluses look more like T's at that point. So let's go plus, 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 plus. Because that electron cloud around hydrogen is very small and it's very large around the oxygen, and so we get a lot more. And then of course our classic example for this is of course drawing water, because water is the classical substance, or the most obvious and most seen substance for, you know, hydrogen bonding. And so we get these big networks of water molecules attracted to each other. So it's got all the same properties as normal dipole-dipole interactions, it's just stronger. Yes?
Okay, now why does this vary with, like in our micro books, it talks about hydrogen bonding being weaker, it's a complete opposite. Why is it
Weaker than what?
it's whenever this says it's weakest, but this is it's weaker compared to like covalent bonds.
Because remember, so here we'll go a slide. So remember, there's intermolecular forces, right? And then there's intramolecular. And so your book is maybe not making a big differentiation between that. Remember, intramolecular is between atoms. This is between molecules. This is generally considered covalent or ionic, right? Meaning if it's between a nonmetal and a nonmetal, and this is between a metal and a nonmetal. Remember, this is between molecules, so you know, it's like this, right? And so this line here, that's a covalent bond. But the dotted line that I might draw to another water molecule, oops, that's what we mean by an H bond. And so when your book is saying hydrogen bonds are weak, it is compared to what's actually holding the two sets of atoms together. But that's kind of comparing apples and oranges. And it's not really that bad as apples and oranges, but it's that we're talking about two different phenomena here. If we're talking about, you know, we're talking about boiling points and melting points and things like that, I don't know what your book's talking about exactly, but if it's comparing the energy to break apart a bond compared to the energy to just separate two molecules, yeah, it is a lot weaker. Said, well, it also depends, and see, here's where we got to be careful. Are we talking about an ionic bond in just like a sodium chloride crystal, or are we talking about an ionic bond in a solution in water, in which case you've got what we're going to talk about next, which is called ion dipole. See, it's all what it's relative to. And it depends on how you're trying to break it too, meaning if you're just trying to break it by heating something up, it's a lot easier usually to, I mean, most organic compounds melt at a lot lower temperature or combust at a lot lower temperature than, say, an ionic compound, right? But now if we're talking about how easy it is to dissolve something, those molecular bonds are pretty hard to separate or break apart, say, in water, whereas ionic compounds pop apart pretty easily because ionic compounds can interact with the hydrogen bonds on the water, right? So if you're thinking along those lines, then yeah, an ionic bond is weak in water because it breaks apart into those ion dipoles. And so it all depends on what perspective you're taking when you're approaching it. If you pay attention when we get to the biochemistry chapters, you'll find that depending upon whether you're a chemist or a biologist or what you're really focusing on, you can use the exact same, or we'll use different words for the exact same things. And that biologists have a different name for everything that we normally know in chemistry too. Now, here's a good question, or here's a request. Show me in your book, is it in micro mostly or is it in Sarasota? Show me in your book where it's talking about it, and maybe we'll go into more detail about what the exact difference is. But if I don't know, I have never taken Well, did I take microbiology? I don't think I took microbiology, and if I did, I certainly don't remember it. I remember taking a genetics course, and I know Todd does genetics, but that's mostly in Bio 112. Anyway, the usages are different. I'm trying to think of another good way to say it. I don't know what would be a good analogy to that. But basically, same words, different circumstances, or focusing on different aspects of things. And so yeah, bring your microbook in here, show me the paragraph or two, and we'll see what they're talking about. I'm guessing they're talking about, like, say, how easy it is to separate something in solution, since most body chemistry is, in water, right? And we're talking about, like, if I have sodium chloride chunk and a chunk of something else, that the sodium chloride is going to be a heck of a lot harder to separate than those other molecules. And so chemists, currently we're focusing more on intermolecular forces than we are on the bonds that hold things together, because we covered that first semester. Good question, though, because that is where there is some overlap between the classes, right? And so we have to be very careful about our usages of it. Todd and I had a couple other good ones where it's like, well, the definition of an electron in Jay's class and the definition of electron in Todd's class and the definition of electron in Sarah's class might be a whole lot different, especially why they're important and stuff, because we're all focusing on different aspects. So excellent question. And we were finishing up hydrogen bonding, right? And I think we've kind of got that. The only thing I'm going to warn you guys is be careful when you're drawing examples for hydrogen bonding versus, say, dipole-dipole. If you use water as an example of dipole-dipole, I'll mark you wrong because it's really hydrogen bonding, right? Even though it is a dipole-dipole interaction, it's better representative of a hydrogen bond, right? Like, for instance, you won't see, like here, notice on the dipole-dipole one, I was very careful to pick HBr, right? Not HF, for instance. So we've got hydrogen bonding. Now, normally we skipped and we said the fourth intermolecular force or kind of interaction that we're going to talk about is ionic, right? We're going to slip one in here. This is called ion dipole. And we really can actually have ion and London dispersion forces mixed up, and there's a lot of different things that we can do that, meaning there's London dispersion forces can be induced by ions and various things like that. We're not going to go much beyond this ion dipole because we see this one pretty frequently. And can you guess what it's between? Yeah, it's between an ion, so a full plus-minus charge, and a partial positive and a partial negative charge. And so, in general, an ion-dipole interaction is going to be stronger than the corresponding dipole-dipole interaction, and it's usually on the order of the same as an ionic attraction, and that's due to geometry considerations. And that's those pictures like when we had, say, sodium chloride dissolved in water, right? Oops, we got to point the water the right way towards it. So this is what we would label an ion dipole to be really specific about it. And then, of course, the hydrogens are attracted to that chlorine because of the partial positives and partial negatives. And so these are also ion dipole interactions. And we'll see that when we make salts of compounds, which means that we basically stick a sodium on there instead of a hydrogen in one spot for types of compounds, that those ion dipole forces are important. And then the last one is ionic. And here's again where, depending upon the book and how picky you want to get, ionic is really more of an intramolecular force, right? Meaning it's between two atoms, meaning we draw it like meaning it's the full positive and negative, and so it's just the attractive force between an Na and a Cl. And I'm calling it an intermolecular force simply because I'm saying that it is an attractive force between two things, and for molecular compounds we have to talk about the attractive force between molecules. But ionic compounds, since by nature they're individual atoms and lattices, then we kind of talk about it as an ionic force. And so that's that gray area. And you could probably throw in covalent someplace in this list too. But again, covalent's talking mostly about between atoms, right? We're talking right now about things between molecules. And we should also, just as a side note, realize that forces 2 through 5 are all electrostatic. And that just points out the whole opposites attract, right? Likes repel. Oops, repel. So that's intermolecular forces in a nutshell. And I suppose I should mention, as I was talking to Brittany earlier, this first test is tough because there's a lot of topics on it. Meaning, certainly naming, certainly reactions, but there's a lot of miscellaneous topics. And some of those topics might show up on this test, and some of those topics might show up in more detail or in different detail on future tests. So like, for instance, if I throw a bunch of questions about Lewis structures and bond angles on the first test, maybe. Could also show up on the second test. Same thing with the intermolecular forces. There might be a question on it on the first test, but the second test, when we get 4 new functional groups that are much more entertaining than the ones that we know now, it'll probably be a bigger part of the test. So some of this material you have to know for 6 chapters because we're going to use it for 6 chapters. Okay, let's take a look at intermolecular forces and how they relate to melting and boiling points. And we always lump melting and boiling points together, but there are some subtle differences between the two. So let's go ahead and take a look at those. So if I compare a melting point to a boiling point. So what transition is melting point? Yeah, it's a solid to a liquid, and boiling point is liquid to gas, right? And I mean, it's the same molecules that we'll be talking about, but how they interact with each other and how they interact with sort of the energy around them kind of varies. What did we say about the energy and, say, a melting point? So the energy is about on the order of the intermolecular forces, right? Meaning something melts when it's got enough energy for those molecules to start moving around and to sort of not necessarily break the intermolecular forces. I say, and I use the word weaken even though I don't like to use it, but essentially they're on par with each other so those molecules can move, whereas for the boiling point the energy is much, much greater than the intermolecular forces, or at least it's great enough that it can separate 2 molecules completely to where they don't interact with each other in the gas, right? And what that means is that the energy for the melting point is basically going into increasing things like vibrations, rotations, and it's just starting in on translations. So a vibration is, if you think about like a guitar string, it vibrates in space. Same thing with molecules, and we'll look at this later in lab. Molecules can vibrate, so those bonds can be thought of as giant springs, and so they're flexible. They can vibrate like this, they can wiggle, they can do all sorts of different motions. And so as we're adding energy to those molecules, that's where the energy is first going to. And then rotations, just it can rotate in space, and so it can have different orientations. And in a solid, all of the molecules are oriented exactly the same, and we start getting into a liquid when those molecules can be oriented in different manners. And then translations is kind of like moving across the space, right? Moving from point A to point B. And so in a solid, those molecules aren't translating. They're not moving at all, really. Whereas in a liquid, we do have some free motion, right? They can move around each other, but they can't come completely separate. Whereas in a gas, they can, right? And so what we see is that in gases, most of the energy is going towards translations. And that's when we talk about the breaking the intermolecular forces. And it doesn't mean that we've broken it like snapped it in half or anything. It just means that we've got so much energy available that they can't interact with each other. And here, when we're talking about those vibrations and rotations, that's kind of that phrasing that I use to say weaken the intermolecular forces. It's not the best phrasing in the entire world, but it kind of works. And so notice that the energy in melting and boiling is going kind of to 2 different places. And so if we take a look at it, it turns out that melting points are very sensitive to the shape of a molecule and the packing between molecules. and that boiling points are less sensitive to shape and packing and more sensitive to the strength of the intermolecular forces. And so what we find is that boiling points are a better indicator of the intermolecular forces between things than melting points. And what we really have to come up from is, and this goes under both columns, is that it's complicated. That as a general rule, we can probably lump boiling points and melting points together. But there will be some occasions where the boiling point might be higher than we expect and the melting point might be lower, or vice versa, due to things like the shape of the molecules and the very specific geometry around them. We see that with cis-trans molecules, and I'll talk about that in a second. And so we're going to have some general rules. We'll make some general statements and realize that we can always find some sort of exception to the rule, or something where it's not the very basic rule that matters, meaning just simply the strength of the intermolecular forces, but we have to factor in shape and geometry. We're not going to focus on it too much. We just want to be aware of it. So let's take a look at the boiling point of alkanes. What we see is that the boiling point is proportional to the size. And that's because alkanes only have London dispersion forces between the molecules. And so if we take a look at it, for instance, between 1 and 4 carbons for an alkane, these are gases. And we're familiar with most of them. We should certainly be able to name them, but we know that methane gas is just natural gas. I have to be honest, we don't see ethane gas terribly much, but certainly you guys have heard of propane, right? And that simply means propane gas is just a 3-carbon molecule, and we use that for heating our houses. And we've heard of butane lighters, and that's a gas. Between about 5 and 16, and I'm going to put that 16, put a question mark there, because it varies a little bit. They're mostly liquids. And the reason it varies is because shape of isomers does play a role. Meaning that one compound that has 16 carbons might be a solid, and then the next compound with 16 carbons in it might be a liquid due to very small differences in their shapes. And we've maybe heard of pentane and hexane. We've kind of used them in class. And then greater than about 16 carbons, we find that they're all solids, meaning that the attractive forces, even though London dispersion forces are weakest, if I take the weakest force times 16 of them, kind of because it's proportional to size, eventually it becomes very large, and then at room temperature at least, those compounds are solids. And so, if we made a plot, we'd see that if I plotted size versus, say, boiling point, that we'd get kind of a linear trend like this. Now, it's not going to be straight linear. There's going to be some zigs and some zags in it, and because shape plays a role in this. And so it's not just that easy. But, we'll also see that, below this temperature, they're solids. In between these two temperatures, they're going to be liquids. And then if you get to a high enough temperature, that's where they're going to be gases. Oops, solid look. Yeah, that's an L, kind of. Not a very good one, but it's there. So really for alkanes, the only thing that matters is London dispersion forces, and so really size is the only thing that we can really look at that's entertaining. We can take a little look at shape. So for instance, what we find is that if I have a cycloalkane, they have boiling points that are on the average of 10 degrees to 20 degrees higher than straight chain. And this is because they stack better. Meaning there is more interaction between two molecules. So the more that those two molecules can get close to each other, the more or the higher, the stronger that attractive force between them is. Question?
Yeah, what's the what?
Straight. So what we're saying is that cycloalkanes tend to have higher boiling points than straight chain alkanes. And that's because they can stack better. So that's where that geometry factor comes in, right? So if you say, for instance, compare something that has 5 carbons as a straight chain with something that has 4 carbons as a cyclic compound, you would go, oh, the straight chain's bigger, it automatically has a higher boiling point. That's not true. We really do have to factor in some subtleties like the shape of the atoms and stuff. The other the other shape one is that if I have something that's linear, that tends to have a higher boiling point than something that's highly branched. And so what we're saying here is that hexane probably has a higher boiling point than, say, butane, or than that. Even though they're both 6 carbons, because the other one is short and squat and kind of globular, whereas the other one is a big long chain, means that they can do it. And that's because if you take a look at it, chains can line up nice and easy, like this. And so there's lots of interaction between the chains. And in fact, that's one of the whole reasons that polymer chemistry exists. And polymer chemistry is one of those things we skip in class. But polymers are basically just long chains of molecules. And those chains can interact with each other, they can wrap around each other. And so polymers have a unique set of characteristics that kind of make them halfway between kind of like a liquid and a solid, meaning things like, think about a garbage bag as a polymer, right? And in fact, polymers can behave more like liquids in that you can get polymers that actually flow, and you can have actually polymers that are actually very hard and behave exactly like solids, depending upon how much the chains interact. And then if I've got a bunch of molecules like this, it's very hard to pack them in tightly. And so there's less interaction here. We'll come back to this in the biology chapters, for instance, when we talk about the difference between straight chain fatty acids versus branched chain fatty acids, or also some of the differences between cis fatty acids and trans fatty acids, because that's kind of where we're going next. So mostly what's important is the number of carbons. Of lesser importance for some of these properties is the packing or the shape of the molecule. So it's just not so easy as saying it's bigger, it's better, but we do have to occasionally factor in shape. Okay, what about alkenes and alkynes? So compared to alkanes, they generally, actually, let's do it this way. I like to be consistent. I like to always, if I'm careful, put the small thing on the left side and the big thing on the right side. Right, Aaron? You forgot math class entirely, but that's okay. Never mind. So if we take a look at, boiling points and melting points, generally alkanes will have a slightly bigger or higher melting point and boiling point. I sometimes like to add this extra line in there. What does that line under the greater than symbol mean? Yeah, they're almost the same. Meaning this really just has 2 or 4 less hydrogen atoms. And so it's not like alkanes are that much heavier or that much bigger than a corresponding alkene and alkyne. And so if you said that if you knew the melting point for, say, hexane, and you can probably guess that the melting point for hexene is probably within a couple degrees of it, meaning they're almost the same. And this is, remember, because London dispersion forces are proportional to mass. or size. So because alkenes and alkynes are missing hydrogen atoms, that means that they're a little bit smaller, so they have a little bit smaller melting points and boiling points in general. Because they're smaller by 2 or 4 hydrogens. I mean, it's not very much, right? But it's a tiny little bit. And so that's maybe a couple degrees Celsius here and there. Frankly, I would lump them and say they're all the same just because they're so close to each other compared to, say, other compounds that'll have bigger differences. Aaron?
I was going to say, is that like a less and an equal sign? You're just emphasizing that's larger, huh?
Well, I'm saying that, I mean, really this is probably the best representation. They're just about equal. I'll be honest, you could also say this, and I wouldn't exactly say you're wrong. You're not 100% right, but you know, they're so close to each other compared to differences between other classes of compounds that we're not going to worry about it for the most part. Now, what is something special about alkenes, though, that we should factor in? Yeah, they have that double bond. What does that allow? So we've been talking, like, for instance, here, really what we're saying is that if we're talking about the difference between linear and highly branched, this is talking about structural isomers, right? Saying that if I've got the linear structural isomer, because those are both 6 carbons long, then it's got a slightly higher boiling point than the other. So what do we have to remember about alkenes and alkynes? They have cis-trans isomers, right? So remember, for all compounds, period, we have structural isomers. For carbon-carbon double bonds specifically, we have cis-trans isomers. And that what we generally find is that the trans isomer has a higher melting point, but the cis isomer has a higher boiling point, which is strange because they have the same size, right? And so they should have the same sort of intermolecular forces between them. But, for example, if I take a look at, say, 1,2-dichloroethane, it's probably the easiest one to look at. If I take a look at the cis versus the trans isomer, and I take a look at the melting point versus the boiling points, for the cis isomer it's minus 80, and for this it's 48. And then I'm going to switch colors just to emphasize it. This is minus 50, so notice this is higher. And this is 60, notice that this is higher. And so it's opposite. One has a higher melting point, the other has a higher boiling point. That's a little strange because it's the same intermolecular forces, right? So we'd expect if one had, say, stronger intermolecular forces, then they both would. And it's because of that part where we said that, for instance, boiling point depends on the intermolecular forces more. Meaning in boiling, we're pulling the molecules really far apart, right? So it does not depend on the packing. And so what we're really doing, and I already drew this picture before, but I'll draw it again because I think seeing things twice is lovely. So which one's cis and which one's trans again? And I'll slow down. I'm kind of starting to speed up a little bit because I got one more topic. Cis, trans. And so if we're talking about boiling point right here, then the cis one is higher, right? Wait. Do I have that? Yeah, this is higher. That makes sense. Duh, Jay. And the reason it's higher is, remember that this is the polar molecule, right? And this is the nonpolar. So it makes sense that the polar molecule has higher intermolecular forces, therefore a higher boiling point. So here's where, you can't just look at the two molecules and say, oh, they're both dipolar or nonpolar. There's a little bit of geometry going on here that we have to factor in. And so if I said that the boiling point of something is higher, the natural response is to also assume that the melting point is higher too, right? Because they're both talking about intermolecular forces. But because boiling points don't care about the packing so much and melting points do, when we talk about our melting point, you want me to go back? I realize I drew those cis-trans fast because I'm good at it. It's what happens when you talk about this stuff for years on end. You get so fast at drawing that it's amazing. I was also talking to someone else. Have you guys ever tried writing and talking at the same time? Is it easy or hard? Yeah, it's really funny how, as a teacher, you've learned to separate those two processes in your brain, and that you get better and better as time goes on. Now, typing and talking at the same time, impossible for me. I can't type because I have to think so hard where the damn keys are on the board, because I never really learned how to type properly. Yeah. Some of you guys are still struggling with chewing gum and walking, I know, and talking and stuff like that. What? That is so harsh, Owen. Because I was thinking of Jess. Just kidding. She's just too quiet over there. We had to draw her into this. So for melting point, remember that it depends on the intermolecular forces, but also on the packing, or basically how close the molecules are to each other. Because remember, melting points are really talking about vibrations and rotations. And so if two things are really stuck next to each other, it's hard for them to rotate. So if we look at the trans, it kind of has this shape. And we can stack those, oops, not a triple bond in there, double bond. We can stack those up nice and easy to each other. And so here we get very tight packing. Therefore, a higher melting point, meaning this one was minus 50. And if we look at the cis isomers, they kind of look like this. And it's a lot harder to pack them because of that bend, unless you line that bend up perfectly. And then you also have to remember that some of them have the opposite bends. And so here we kind of have a looser packing. Therefore, we have a lower melting point. This one was minus 80 degrees. And I guess we should put some units in there. J shouldn't be a total slacker. We know we're talking about degrees Celsius, but we'll put the units in there anyway. So shape plays a role in things, something we have to consider, especially like for cis and trans molecules where one of them might be nonpolar and one of them might be dipolar. That really can change things around. We'll come back to that and we'll see some of those same things happening with other molecules. And really the take-home message is that it's a little bit more complicated than we want it to be probably. And so every once in a while we'll point out a few exceptions to the rules. And so when you're looking at something or you're comparing two molecules and you go like, no, Jay told me this one's got to have the higher boiling point. Well, that might be if you only think about intermolecular forces, but if you start factoring in structure and geometry, you might have to, it makes it more complicated. There's never an easy, this is A and that's B. That would be too easy. That's why chemistry is hard. Okay, one last topic, something we should be familiar with, solubility. What we're just going to do now is we're going to go into it in a little bit more detail and then, worry about it more in later chapters because I got to be honest, alkanes, alkenes, and alkynes aren't terribly interesting for solubility, are they? What was our general rule from chapter 14? Yeah. What we basically said is like dissolves like. And what did we mean by the like part? What has to be a like? Yeah, the intermolecular forces. And so what we're really doing is we're comparing intermolecular forces. And that really is a pretty good rule of thumb. And it probably gets you the right answer at least 95% of the time. maybe 75, you know, someplace in there. It's a pretty good rule. We want to expand on that just a little bit and think about what's actually happening when we dissolve something. So we're going to want to take a look at a little more detailed picture. And we're also going to kind of think about it in terms of the energy involved. And so if we take a look at it, there's three processes occurring. And it's the interaction between those three processes that tell us whether something that will dissolve or not. We've got solute-solute interaction. So for instance, I'm going to do, my example is pentane dissolved in water. So in order to dissolve pentane, we have to break here intermolecular or London dispersion forces. And so this is our solute and our solute. If you forgot what the terms solute, solvent, and solution mean, remember solute is what we have the smaller amount of, solvent is the larger amount, and then solution is the mixture of the two. So if we're dissolving this in water, that means that water is our solvent. That's a crappy looking water molecule. There, we'll do it like this. It's not the best looking water molecule. So this is solvent, solvent. And here what I have to do is break hydrogen bonds between the water molecules, right? Meaning in order to squeeze something in between them, to say it's dissolved in water, meaning it's surrounded by the water, I have to first pull apart the alkane part, then I have to pull apart the water part, and then that third process, which is a little bit different, is between our solute and our solvent. I have to kind of make the pentane interact with the water. And we don't really have a term for London dispersion interacting with a hydrogen bond. You know, it's kind of LDF H bonds. But we do know that those are, so that we have to form these London dispersion force / hydrogen bond intermolecular forces. And what we know energetically is that this is very easy. These are very hard to break, and so that means that these both require energy. And the idea behind things dissolving is it takes energy to separate everything together, but then when I put it back together, what happens here is I recoup the energy. Except because these don't mix, therefore there's no energy regained. So the idea is it takes a lot of energy to separate all those molecules, and you don't gain any of that energy back by forming new hydrogen bonds or London dispersion forces or anything. And so if we kind of summarize it, and I would put this below this, but I'm going to kind of keep it on the same slide. What we're saying is that the energy to separate them is much greater than the energy that we get from mixing them together. And so if the energy to separate all those particles out is so much larger than the energy that we would get back by mixing them together, it doesn't happen. And that's why when you look at a test tube, we get two layers. We get a layer of, say, pentane, where we just have London dispersion forces, and we get a layer of water, which is all hydrogen bonding, and the two don't mix. Because there's no reason that a hydrogen bond would prefer to be next to something that is capable of doing London dispersion forces. Positive and negatives want to be by positive and negatives. Things that are neutral want to be by things that are neutral. I'd argue it's even more a case of the water just doesn't like the hexane. The hexane probably doesn't care one way or the other. So we know that pentane won't dissolve in water, that alkanes are pretty insoluble. What if we consider something that we know does dissolve in water, which is NaCl? We know that this is very soluble. So if we take a look at those same things, we know that we've got our Na plus and our Cl minus. This is ionic. We know that we have the water from above, That's still hydrogen bonding. So it takes energy required to separate these. And then remember, our last step is if I mix them up. And that's where we see that we can mix them up pretty easily because the hydrogens from water can interact with the chlorines and the oxygens interact with those sodiums. Oops. Let's just draw water up here. And we've got all those partial positives and partial negatives going on. And so here, that energy to mix is really an example of, remember these are ion dipole interactions. And so the energy to mix is large. Therefore, if we kind of put it in terms of energy, the energy to separate them is less than the energy that we get from mixing them together. Therefore, they're soluble. So solubility really comes down to whether it's energetically favorable to break everything apart and mix it together or not. And so if the intermolecular forces are alike, that energy that we get from mixing is larger than the energy it takes to separate all those molecules apart. And if the intermolecular forces are different, then that energy we get from mixing is very small. And so the take-home message from this is that process one, like dissolves like, that'll get you the answers, okay? This is a much more detailed description and explanation. And so what should we expect for the solubility of alkanes, alkenes, and alkynes? So, meaning ignoring part one and part two, the real, what do you need to know? Alkanes, enes, and ynes are not soluble because London dispersion forces are not like hydrogen bonds. And so that really is the whole take-home message, meaning we're really looking at the intermolecular forces when like dissolves like. That whole idea of breaking apart it into three different processes, that's the real underlying explanation for it. So explanation one will get you the answer 90% of the time. Explanation two will also get you the right answer, but it also is a more complicated explanation. Do you want me to go back a slide at all? We can. I mean, that's the whole point of doing that. And really, that's the last statement that I wanted to say. So we talked mostly about intermolecular forces, but then we also looked at how intermolecular forces tell us about melting points and boiling points, and how intermolecular forces are also responsible for solubility. And hopefully some of that's review. Hopefully the molecular forces stuff is pretty fresh in your brain from last semester. And hopefully since you've now heard it a bunch of times, it'll be better and things like that. So what have we got going on for the rest of the week? So chapter 20, B and C were due today, right? Or what was it? Actually, C was due yesterday, technically. Oh yeah, that's right, because I mixed up the aromatics and crap. And so let's make 20D due tomorrow. That way I can get it back to you graded. Plus you have the entire day to ask me questions. And frankly, I think it's a pretty short worksheet. It should only take a few minutes, I think. And then on Thursday in class, we're going to just review, ask questions, etc. On Friday, we're going to start in on chapter 22, naming. That's alcohols and ethers. Monday, we of course have our, Sunday night. Do people want to have a review for things Sunday? And it doesn't have to be Sunday night. If you want to do it Sunday at 3 o'clock, so it's before the Super Bowl, that's fine too. I don't really care. I'm not watching the Super Bowl probably. So what time on Sunday would people want to get together? If you don't have to even come. If no one wants to come, it's fine. I'm okay with chilling out at home with my dog. What time on Sunday do we want? Afternoon or evening? How many people want, if you have a preference, afternoon or evening? What? So 6 o'clock? I don't know when the Super Bowl even starts.
4 o'clock.
What is your problem, Owen? Okay, 6 o'clock for review. And then, of course, Monday we're going to have the exam on Chapter 19 and 20. You can show up as early as 7:15, and you can, of course, work until 9:15. And again, I don't know if it'll take 2 hours. I don't think so. I've gotten better at writing tests that are smaller. But